Okay, so today we're doing the structural analysis for the recovery bulkhead. We're using a method called finite element analysis, which is there's a bunch of different solvers that can do it. SolidWorks does it. More commonly used is ANSYS. I'm a bit more familiar with ANSYS, so I'm going to be going through the ANSYS methodology, but once you kind of learn one, you kind of know them all. So this is the assembly we want to analyze. You can analyze assemblies or parts. And the first step is basically creating your geometry. So what I did, let's show you the finished product, which is this modified bulkhead. It is pretty much exactly the same, but I took out these screws that are here. And I think I took out some set screws. So basically all that's in this model is the bulkhead and the two retention pins. I have not modeled the eye bolts because I have had, when I did a previous model, it was hard to get that interaction to model correctly. So I also did not model those. Okay, so basically took those guys out, and then not sure where these, basically all those got cut. So if you do an assembly, you kind of want to take out any unnecessary parts. Like for example, these don't really add much structurally, so we can take them out because you can see this has a number of extra faces and you're just adding more bodies. The more interactions you add, it's more complex. So if you can delete things, definitely do. However, I do not want to delete these pins because obviously they interact with the bulkhead. These fasteners, not so much. In some cases, you will have fasteners that like take a lot of load. For example, the ones that mount the fins to the fin cage, they have like preload and they're kind of like taking a lot of load. So we do model those fasteners. But if you want to model fasteners, you should delete the threads and simplify the head. So in this case, I would just model this as like a solid cylinder and like say delete all of those faces if you can. So once you have simplified your assembly, if you have an assembly, if you have a part that's not necessary, you basically save as a step file. So you just change to step, and under options, make sure you have not clicked this option. This is like a default, but basically it will split like every circular face in two, and it's just kind of annoying later on. And then you'll save it. I've already done this, so we can skip that step. And that completes your geometry. Is there any questions about that? Okay. So you can also make geometry in ANSYS, and if you look at like beginner tutorials, they might like do that because they'll do like very simple parts, but you should always just like import your CAD models basically. So if you open up Workbench, which if you install ANSYS, by the way, and you try to search in your search bar for ANSYS, the right thing won't come up. You want to search for Workbench and then open up Bench. You get a barrage of options here. You can do like CFD, vibration simulations. What we're doing today is a static structural simulation. So you can just drag and drop and it will load. So you can drag and drop any of these. Sometimes you'll have coupled systems where you can have like multiple of these. That's going to be on the scope. So the first thing is, so pretty much to do this simulation, you do these 2, 3, 4, 5, 6, and 7, and then some of these steps kind of just automatically are done. This engineering data is just, if in case you use like a very specialty material and you need to create a new material, you'll have to go in there and give the material properties. However, since we're just using like aluminum and steel, you don't need to do that. But for example, for composites, they'll vary from part to part. You'd have to go and insert your data in there, which would be like Young's modulus and stuff. However, we can switch right to geometry. So if you do not double click on geometry, but if you double click, it will take you to space claim, which I don't really like. I mean, you can use if you want, but I prefer design modeler. So if you right click new design modeler, it will load. And so, yeah, so you'll see like extrude, revolve, sweep, blah, blah, blah. So you can make bad models in here, but do not do that. It's giant pain. So you need to go file, import external geometry file, and click on your step file you made. So nothing happens because for some reason in ANSYS, you need to like, once you need to do something and then you need to hit the generate button. So if there's a green check mark, you're good. But if there's a lightning bolt, you need to click on it and click generate. So there's our import, and we've imported 3 bodies, which makes sense, the bulkhead and then the 2 retention pins. So successful import. I'm going to go ahead and save. Which, in case you're curious, there's a separate simulations folder on the GrabCAD. So I'm just going to call this bulkhead. Ideally, add date is the 8th of June. And that's all you need to do for the geometry. I was just gonna save, I'll let that save. Close this window. So far, making sense? Okay, so now the model is kind of like the meat of it. So if we double click on model. Takes a second to load. I'm also doing this off the cuff, so I can't promise that it will actually work or solve today. Sometimes that's just like how it goes. You need to do it multiple times. Okay, so there we go. So you see geometry imports, which is just like our import geometry, which is our 3 bodies, materials. So we need to add, so the pins are steel, which is fine, but we need the aluminum bulkhead. So if you click on materials, you can search for things. So if I just search like aluminum alloy, so I'm just gonna click plus. So now there are 2 materials. So retention pin, structural steel, retention pin, structural steel, but we have to go in and change the bulkhead, material, assignment, aluminum alloy. And so now we have all our materials because the solver needs to know like mechanical data and how those, modules and all that. So the next thing we have to do is connections. So when you have multiple parts, you have to tell the solver how they interact. Because otherwise the solver is not going to know like, oh, maybe these pins can penetrate the bulkhead, or maybe they can spin freely. So these pins in the configuration we have, they should not be able to move really, if I'm correct, right? This set screw prevents it from rotating and translating. Okay, we will assume that is true. So connections, insert. So I do a manual contact region. So contact versus target, I do not think matters. So for the contact, I'll say I'm going to select all the basically all the faces where oops. Okay, so now we have our pins. So these four faces are the ones that are in contact with the bulkhead. So I'm going to select those four, hit apply. I'm going to right click, invert visibility. So now I can just see the bulkhead. And I'm going to select the faces where it contacts. So if you control click, that's how you get multiple selections. Target Y. And the type is going to be I think they're essential. So basically the pins, we want to tell the solver that the pins cannot penetrate the bulkhead, but technically they can slide. So we're going to call it a frictional contact. Basically, the friction is with no penetration, but those faces can slide relative to each other. I'm going to add 361. And I'm going to go show all bodies. Okay, so now so now we have shown how the pins and the bulkhead interact, but now we need to tell the solver like how these parts can kind of move in space. So these pins, like they should not yet be able to be slid. Like they'll be blown out later, but they're not like sliding around during flight. So what I'm going to do is I'm going to hide that. I'm going to give a actually, we should just add a mesh first. So if I show all bodies, click on mesh, we're just going to generate the default mesh. And we'll come back to that. You can kind of do the mesh in any order. Hide that. So boundary conditions. If you right click on static structural, you'll insert. It comes with all these force, pressure, acceleration. So basically we want to say that those like cylinder faces, they're pretty much fixed. So I'm going to add a fixed support to these, apply, show bodies. So now these are kind of, they cannot penetrate through the bulkhead and they are fixed at that. The next, the bulkhead, you have to remember you have to fix your part or your assembly in space somehow. Because right now, if I were to add a force, it would just like fling off to infinity. So what is keeping this fixed is the radial holes. So I'm going to insert another fixed support. Going on all the radial holes. You kind of have to, this is definitely, in my opinion, the hardest part about FEA, thinking about how your body interacts with like the space and the other bodies in your assembly if you have them. So I've selected all the radial holes and under geometry, hit apply. So 8 faces. You can see they're selected in purple. So we have the bulkhead fixed in space, we have the pins fixed in space, and we have the interaction. So now we need a load. So I think right now the drove is worst case 16 Gs. So on static structural, if we go insert, typically I add forces, but I think we'll add acceleration. And the magnitude will be 16 times 9.81. Okay, I lied. We're not going to want to add an acceleration because, okay, never mind. I think you can only, if you want to add a load to a specific face, I think you need a force or a moment, and acceleration will work, I guess. So 16 Gs, 16 times 9.81, and I'm gonna estimate, so the dry mass is like 17 kilos, and then the nose magpie is like 2 kilograms. So I'm gonna say 15. So 2,300 newtons is what we'll simulate. So static structural insert, we will do a force. I'm gonna hide. Okay, so I'm gonna apply, this split's kind of funny, but I want to apply the force to the whole pin face, if that makes sense, because the drove will pull on those two pins. Why? So the magnitude is 2,300, and so the direction being the positive. Okay, define, instead of defined by vector, defined by components. So for now, I'm going to simulate that the total force is straight up, but there is a tether, right? So the load kind of pulls on an angle on both of these. So for now, we'll say, so you have your coordinate system here. You'll have 2,300 newtons into Z. Ramped just means basically it does a simulation over a time step, and it just applies the load linearly, and then you get the result at the end of the time step. The ramp is just like, it helps it solve it better, I believe. So show all bodies, so we've added our load. So now, and we've added our mesh. So now we're pretty much good to go. So we go back to our, well, I'll just pause. Does that make sense? So geometry, materials, contacts, if you need them, boundary conditions. Every single simulation needs boundary conditions. Like we would still, even if this didn't have like the pins, we would still need to fix the bulkhead in space. And mesh. So mesh kind of, it's kind of difficult to like give you a specific way to do the mesh. But one really good way, if you do, if your simulation is not too like computationally intensive, is adaptive meshing. So basically you're looking to get your mesh fine enough that it solves the solution, and making the mesh any finer does not change the solution. Because as you, it's kind of like a resolution, like as you make all these little triangles smaller, you get a better solution, but there's eventually there's like a mesh size that if you keep going any smaller, the solution doesn't get any better. And so you can either kind of do this by hand, but ANSYS has adaptive meshing. So to do that, you need to go into your solution. So we're looking for the maximum stress in this case. That's like our primary mode of concern. So they give you all these values. Basically, you use the equivalent, the von Mises stress. There's a couple different failure criteria, basically. And the von Mises one is pretty much the one most common used for like ductile materials, so aluminum and stuff like that. You only have to consider the maximum principle, I think, is usually used for like brittle materials, and I'm not quite sure what the other ones do. So generally, just look at the von Mises stress. And then once you have that equivalent stress field under solution, you can insert convergence. And so if we say the allowable change is 5%, I think that's all you need to do. We'll try running it and see what happens. So that basically would mean like the change between iterations is like 5%. So once the error between like mesh size versus like, it will basically calculate the stress. And then if going up the mesh size, the next stress is like less than a 5% change, you converged. I hope I remember how to do that. We will hit solve and see what happens. Sometimes you get these warnings, and usually they're just okay, contact status. This might not be good. A lot of times it does not work on the first time, and you have to kind of adjust as you go. But let's see. And I've done one solution, so it's calculate the maximum stress, number of nodes, number of elements, and it's going to iterate on that until we get to a 5% change between iterations. So now you can see there's already a ginormous change between the first and second stress. So the mesh was not good enough, basically. So it means it still needs to converge, but how you interpret your results is you open your solution and you get this color plot basically, which shows you like stress maps. So your in this solution, the maximum stress was like 0.2 megapascals. So then you need the yield stress of that material. So if we yield stress aluminum, 275. Oh, actually, sorry, I misspoke. This is 226 megapascals. So we are just below the yield. The yield is the point at which the material is going to permanently deform. So you want to like avoid that, especially for something like this. If that bulkhead permanently deforms on drove deployment, then the pins might get lodged in. So that's why we want to avoid yielding. But technically the part will break at fracture. So if you go over the yield stress, you just will have a slightly deformed part, not necessarily like a quote unquote broken part, but usually it's considered to have failed if it's yield, because you want a decent safety factor. So the adaptive meshing did not work because we ran into numerical limits because we're using ANSYS student. So I'm going to run this without adaptive meshing, and then further, this will probably be redone in either SolidWorks or Siemens or something that we have licensing to do more mesh elements. So if you go to mesh, right click, insert sizing, I should also mention up here is your like kind of selection, you know, you would call this. So you can select it so it only vertices, edges, faces, or entire bodies. I'm going to switch it to bodies because I want basically all these with the same size. I'm going to try 0.001. And we'll just see what happens. Generally, when you add the sizing, it will be a bit more even.